Bolted repairs are not desirable for honeycomb sandwich structure due to the limited bearing strength of the thin face sheets and weakened honeycomb structure from drilling holes. The advantage of a bolted repair is that you need to select only patch material and fasteners, and the repair method is similar to a sheet metal repair. There is no need for curing the repair and storing the prep-reg repair material and film adhesives in a freezer. Patches may be made from aluminum, titanium, steel, or pre-cured composite material. Composite patches are often made from carbon fiber with an epoxy resin or fiberglass with an epoxy resin. You can repair a carbon fiber structure with an aluminum patch, but you must place a layer of fiberglass cloth between the carbon part and the aluminum patch to prevent galvanic corrosion. Titanium and pre-cured composite patches are preferred for repair of highly loaded components. Pre-cured carbon/epoxy patches have the same strength and stiffness as the parent material as they are usually cured similarly. Titanium or stainless steel fasteners are used for bolted repairs of a carbon fiber structure. Aluminum fasteners corrode if used with carbon fiber. Rivets cannot be used because the installation of rivets using a rivet gun introduce damage to the hull and surrounding structure, and rivets expand during installation, which is undesirable for composite structures because it could cause delamination of the composite material. Repair procedures. Step 1. Inspection of the damage. The tap test is not effective to detect delamination in thick laminates unless the damage is close to the surface. An ultrasonic inspection is necessary to determine the damage area. Consult the SRM to find an applicable NDI procedure. Step 2. Removal of the damage. The damaged area needs to be trimmed to a round or rectangular hole with large smooth radii to prevent stress concentrations. Remove the damage with a sander, router, or similar tool. Step 3. Patch preparation. Determine the size of the patch based on repair information found in the SRM. Cut, form, and shape the patch before attaching the patch to the damaged structure. It is easier to make the patch a little bigger than calculated and trim to size after drilling all fastener holes. In some cases, the repair patches are stocked pre-shaped and pre-drilled. If cutting is to be performed, standard shop procedures should be used that are suitable for the patch material. Titanium is hard to work and requires a large, powerful slip roller to curve the material. Metal patches require filing to prevent crack initiation around the cut edges. When drilling pilot holes in the composite, the holes for repair fasteners must be a minimum of 4 diameters from existing fasteners and have a minimum edge distance of 3 fastener diameters. This is different from the standard practice for aluminum of allowing a 2 diameter distance. Specific pilot hole sizes and drill types to be used should follow specific SRM instructions. Figure 7.75. Step 4. Hole pattern layout. To locate the patch on the damaged area, draw 2 perpendicular centerlines on the parent structure and on the patch material that define the principal load or geometric directions. Then, lay out hole pattern on the patch and drill pilot holes in the patch material. Align the 2 perpendicular centerlines of the patch with the lines on the parent structure and transfer the pilot holes to the parent material. Use Clecos to keep the patch in place. Mark the edges of the patch so that it can be returned to the same location easily. Step 5. Drilling and reaming holes in patch and parent structure. Composite skins should be backed up to prevent splitting. Enlarge the pilot holes in the patch and parent materials with a drill 1/64 undersize and then ream all holes to the correct size. A tolerance of plus 0.0025/0.000 inch is usually recommended for aircraft parts. For composites, this means interference fasteners are not used. End of page 7-44. Step 6. Fastener installation. Once fastener holes are drilled full size and reamed, permanent fasteners are installed. Before installation, measure the fastener grip length for each fastener using a grip length gauge. As different fasteners are required for different repairs, consult the SRM for permissible fastener type and installation procedure. However, install all fasteners wet with sealant and with proper torque for screws and bolts. Step 7. Sealing of fasteners and patch. Sealants are applied to bolted repairs for prevention of water/moisture intrusion, chemical damage, galvanic corrosion, and fuel leaks. They also provide contour smoothness. The sealant must be applied to a clean surface. Masking tape is usually placed around the periphery of the patch, parallel with the patch edges and leaving a small gap between the edge of the patch and the masking tape. Sealing compound is applied into this gap. Step 8. Application of finish coat and lightning protection mesh. The repair needs to be sanded, primed, and painted with an approved paint system. A lightning protection mesh needs to be applied if composite patches are used in an area that is prone to lightning strikes. Fasteners used with composite laminates. Many companies make specialty fasteners for composite structures, and several types of fasteners are commonly used: threaded fasteners, lock bolts, blind rivets, and specialty fasteners for soft structures such as honeycomb panels. The main differences between fasteners for metal and composite structures are the materials and the footprint diameter of nuts and collars. Corrosion precautions. Neither fiberglass nor Kevlar fiber reinforced composites cause corrosion problems when used with most fastener materials. Composites reinforced with carbon fibers, however, are quite cathodic when used with materials such as aluminum or cadmium, the latter of which is a common plating used on fasteners for corrosion protection. Fastener Materials. Titanium alloy T6L4V is the most common alloy for fasteners used with carbon fiber reinforced composite structures. Austenitic stainless steels, superalloys, e.g., E286, multiphase alloys, e.g., MP35N or MP159, and nickel alloys, e.g., alloy 718, also appear to be very compatible with carbon fiber composites. Fastener System for Sandwich Honeycomb Structures, SPS Technologies Tite. The Adjustable Sustained Preload (ASP) fastening system provides a simplified method of fastening composite, soft core, metallic or other materials, which are sensitive to fastener clamp-up or installation force conditions. Clamping force can be infinitely adjustable within maximum recommended torque limits, and no further load is applied during installation of the lock collar. The fastener is available in two types. The ASP has full shank and the 2ASP has a pilot-type shank. Figures 7, 76 and 7 to 77. Hi-Lok and Huck-Spin Lockbolt fasteners. Most composite primary structures for the aircraft industry are fastened with Hi-Loks, Hi-Shear Corporation, or Huck-Spin Lockbolts for permanent installations. The Hi-Lok is a threaded fastener that incorporates a hex key in the threaded end to react to the torque applied to the collar during installation. End of page 7 to 45. The collar includes a frangible portion that separates at a predetermined torque value. Figure 7, 78. The lockbolt incorporates a collar that is swaged into annular grooves. It comes in two types, pull and stump. The pull type is the most common, or a frangible pintail is used to react the axial load during the swaging of the collar. When the swaging load reaches a predetermined limit, the pintail breaks away at the breakneck groove. The installation of the Hi-Lok and the pull-type Huck-Spin lockbolt can be performed by one technician from one side of the structure. The stump-type lockbolt, on the other hand, requires support on the head side of the fastener to react the swage operation. This method is usually reserved for automated assembly of detail structure in which access is not a problem. The specific differences in these fasteners for composite structure in contrast to metal structure are small. For the Hi-Lok, material compatibility is the only issue. Aluminum collars are not recommended. Standard collars of A286, 303 stainless steel, and titanium alloy are normally used. The Huck-Spin lockbolt requires a hat-shaped collar that incorporates a flange to spread the high bearing loads during installation. The lockbolt pin designed for use in composite structure has 6 annular grooves as opposed to 5 for metal structure. Figures 7, 79 and 7 to 80. Eddy bolt fasteners. Eddy bolt fasteners, Alcoa, are similar in design to Hi-Loks and are a natural choice for carbon fiber composite structures. The eddy bolt pin is designed with flutes in the threaded portion, which allow a positive lock to be made during installation using a specially designed mating nut or collar. End of page 7 to 46. The mating nut has 3 lobes that serve as driving ribs. During installation, at a predetermined preload, the lobes compress the nut material into the flutes of the pin and form the locking feature. The advantage for composite structure is that titanium alloy nuts can be used for compatibility and weight saving without the fear of galling. The nuts spin on freely, and the locking feature is established at the end of the installation cycle. Figure 781. Cherry ZZ Buck, CSR 90433, Hollow Rivet. The Cherry Hollow and EZ Buck Rivet is made from titanium/columbium alloy and has a shear strength of 40 ksi. The EZ Buck Rivet is designed to be used in a double flush application for fuel tanks. The main advantage of this type of rivet is that it takes less than half the force of a solid rivet of the same material. The rivets are installed with automated riveting equipment or a rivet squeezer. Special optional dies ensure that the squeezer is always centered during installation, avoiding damage to the structure. Figure 782. Blind fasteners. Composite structures do not require as many fasteners as metal aircraft because stiffeners and doublers are co-cured with the skins, eliminating many fasteners. The size of panels on aircraft has increased in composite structures, which causes backside inaccessibility. Therefore, blind fasteners or screws and nut plates must be used in these areas. Many manufacturers make blind fasteners for composite structures, a few are discussed below. End of page 7 to 47. Blind bolts. The Cherry MaxiBolt is available in titanium for compatibility with composite structures. The shear strength of the MaxiBolt is 95 ksi. It can be installed from one side with a G83 or equivalent pneumatic hydraulic installation tool, and is available in 100 degrees flush head, 130 degrees flush head and protruding head styles. Figure 783. The Alcoa UABTM blind bolt system is designed for composite structures and is available in titanium and stainless steel. The UABTM blind bolt system is available in 100 degrees flush head, 130 degrees flush head, and protruding head styles. The Hi-Lok TM blind fastening system is designed specifically for use in composite structures in which access is limited to one side of the structure. It combines high joint preload with a large diameter footprint on the blind side. End of page 7 to 48. The large footprint enables distribution of the joint preload over a larger area, virtually eliminating the possibility of delaminating the composite structure. The shear strength of the Hi-Lok TM is 95 ksi, and it is available in 100 degrees flush head, 130 degrees flush head, and protruding head styles. A similar fastener designed by Monogram is called the Radiolock. Figure 784. Fiberlite. The Fiberlite fastening system uses composite materials for a wide range of aerospace hardware. The strength of Fiberlite fasteners is equivalent to aluminum at 2/3 the weight. The composite fastener provides good material compatibility with carbon fiber and fiberglass. Screws and nut plates in composite structures. The use of screws and nut plates in place of Hi-Loks or blind fasteners is recommended if a panel must be removed periodically for maintenance. Nut plates used in composite structures usually require 3 holes, 2 for attachment of the nut plate and 1 for the removable screw, although rivetless nut plates and adhesive bonded nut plates are available that do not require drilling and countersinking 2 extra holes. Machining processes and equipment. Drilling. Hole drilling in composite materials is different from drilling holes in metal aircraft structures. End of page 7 to 49. Different types of drill bits, higher speeds, and lower feeds are required to drill precision holes. Structures made from carbon fiber and epoxy resin are very hard and abrasive, requiring special flat flute drills or similar 4-flute drills. Aramid fiber, Kevlar/epoxy composites are not as hard as carbon but are difficult to drill unless special cutters are used because the fibers tend to fray or shred unless they are cut clean while embedded in the epoxy. Special drill bits with clothespin points and fishtail points have been developed that slice the fibers prior to pulling them out of the drilled hole. If the Kevlar/epoxy part is sandwiched between 2 metal parts, standard twist drills can be used. Equipment. Air-driven tools are used for drilling holes in composite materials. Drill motors with free speed of up to 20,000 revolutions per minute are used. A general rule for drilling composites is to use high speed and a low feed rate, pressure. Drilling equipment with a power feed control produces better hole quality than drill motors without power feed control. Drill guides are recommended, especially for thicker laminates. Do not use standard twist drill bits for drilling composite structures. Standard high-speed steel is unacceptable because it dulls immediately, generates excessive heat, and causes ply delamination, fiber tear-out, and unacceptable hole quality. Drill bits used for carbon fiber and fiberglass are made from diamond-coated material or solid carbide because the fibers are so hard that standard high-speed steel (HSS) drill bits do not last long. Typically, twist drills are used, but brad point drills are also available. The Kevlar fibers are not as hard as carbon, and standard HSS drill bits can be used. The hole quality can be poor if standard drill bits are used, and the preferred drill style is the sickle-shaped clank drill. This drill first pulls on the fibers and then shears them, which results in a better quality hole. Larger holes can be cut with diamond-coated hole saws or fly cutters, but only use fly cutters in a drill press, and not in a drill motor. Figures 7, 85 and 7, 86, and 7 to 87. Processes and precautions. Composite materials are drilled with drill motors operating between 2,000 and 20,000 revolutions per minute and a low feed rate. Drill motors with a hydraulic dash pod or other type of feed control are preferred because they restrict the surging of the drill as it exits the composite materials. This reduces breakout damage and delaminations. Parts made from tape products are especially susceptible to breakout damage. Parts made from fabric material have experienced less damage. End of page 7 to 50. The composite structure needs to be backed with a metal plate or sheet to avoid breakout. Holes in composite structures are often pre-drilled with a small pilot hole, enlarged with a diamond-coated or carbide drill bit and reamed with a carbide reamer to final hole size. Back counterboring is a condition that can occur when carbon/epoxy parts made metal substructure parts. The back edge of the hole in the carbon/epoxy part can be eroded or radiused by metal chips being pulled through the composite. The condition is more prevalent when there are gaps between the parts or when the metal debris is stringy rather than small chips. Back counterboring can be minimized or eliminated by changing feeds and speeds, cutter geometry, better part clamp up, adding a final ream pass, using a peck drill, or combination of these. When drilling combinations of composite parts with metal parts, the metal parts may govern the drilling speed. For example, even though titanium is compatible with carbon/epoxy material from a corrosion perspective, lower drilling speeds are required in order to ensure no metallurgical damage occurs to the titanium. Titanium is drilled with low speed and high feed. Drill bits suitable for titanium might not be suitable for carbon or fiberglass. Drill bits that are used for drilling titanium are often made from cobalt vanadium. Drill bits used for carbon fiber are made from carbide or are diamond-coated to increase drill life and to produce an accurate hole. Small-diameter high-speed steel drill bits, such as number 40 drill, which are used to manually drill pilot holes, are typically used because carbide drills are relatively brittle and are easily broken. The relatively low cost of these small HSS drill bits offsets the limited life expectancy. High-speed steel drill bits may last for only one hole. The most common problem with carbide cutters used in hand drill operations is handling damage, chipped edges, to the cutters. A sharp drill with a slow constant feed can produce a 0.1 mm, 0.004 inch, tolerance hole through carbon/epoxy plus thin aluminum, especially if a drill guide is used. With hard tooling, tighter tolerances can be maintained. When the structure under the carbon/epoxy is titanium, drills can pull titanium chips through the carbon/epoxy and enlarge the hole. In this case, a final ream operation may be required to hold tight hole tolerances. Carbide reamers are needed for holes through carbon/epoxy composite structure. In addition, the exit end of the hole needs good support to prevent splintering and delaminations when the reamer removes more than about 0.13 mm, 0.005 inch, on the diameter. The support can be the substructure or a board held firmly against the back surface. Typical reaming speeds are about 1/2 of the drilling speed. Cutting fluids are not normally used or recommended for drilling thin, less than 6.3 mm, or 0.25 inch thick, carbon/epoxy structures. It is good practice to use a vacuum while drilling into composite materials to prevent carbon dust from freely floating around the work area. Countersinking. Countersinking a composite structure is required when flush head fasteners are to be installed in the assembly. For metallic structures, a 100 degrees included angle shear or tension head fastener has been the typical approach. In composite structures, two types of fasteners are commonly used, a 100 degrees included angle tension head fastener or a 130 degrees included angle head fastener. The advantage of the 130 degrees head is that the fastener head can have about the same diameter as a tension head 100 degrees fastener with the head depth of a shear type head 100 degrees fastener. For seating flush fasteners in composite parts, it is recommended that the countersink cutters be designed to produce a controlled radius between the hole and the countersink to accommodate the head-to-shank fillet radius on the fasteners. In addition, a chamfer operation or a washer may be required to provide proper clearance for protruding head fastener head-to-shank radii. Whichever head style is used, a matching countersink/chamfer must be prepared in the composite structure. Carbide cutters are used for producing a countersink in carbon/epoxy structure. These countersink cutters usually have straight flutes similar to those used on metals. For Kevlar fiber/epoxy composites, S-shaped positive rake cutting flutes are used. If straight fluted countersink cutters are used, a special thick tape can be applied to the surface to allow for a clean cutting of the Kevlar fibers, but this is not as effective as the S-shaped fluted cutters. Use of a piloted countersink cutter is recommended because it ensures better concentricity between the hole and the countersink and decreases the possibility of gaps under the fasteners due to misalignment or delaminations of the part. Use a microstop countersink gauge to produce consistent countersink wells. Do not countersink through more than 70% of the skin depth because a deeper countersink well reduces material strength. When a piloted countersink cutter is used, the pilot must be periodically checked for wear, as wear can cause reduction of concentricity between the hole and countersink. This is especially true for countersink cutters with only one cutting edge. For piloted countersink cutters, position the pilot in the hole and bring the cutter to full RPM before beginning to feed the cutter into the hole and preparing the countersink. If the cutter is in contact with the composite before triggering the drill motor, you may get splintering. End of page 7 to 51. Cutting processes and precautions. Cutters that work well for metals would either have a short life or produce a poorly cut edge if used for composite materials. The cutters that are used for composites vary with the composite material that is being cut. The general rule for cutting composites is high speed and slow feed. 1. Carbon fiber reinforced plastics. Carbon fiber is very hard and quickly wears out high-speed steel cutters. For most trimming and cutting tasks, diamond grit cutters are best. Aluminum oxide or silicon carbide sandpaper or cloth is used for sanding. Silicon carbide lasts longer than aluminum oxide. Router bits can also be made from solid carbide or diamond coated. 2. Glass fiber reinforced plastics. Glass fibers, like carbon, are very hard and quickly wear out high-speed steel cutters. Fiberglass is drilled with the same type and material drill bits as carbon fiber. 3. Aramid, Kevlar, fiber reinforced plastics. Aramid fiber is not as hard as carbon and glass fiber, and cutters made from high-speed steel can be used. To prevent loose fibers at the edge of aramid composites, hold the part and then cut with a shearing action. Aramid composites need to be supported with a plastic backup plate. The aramid and backup plate are cut through at the same time. Aramid fibers are best cut by being held in tension and then sheared. There are specially shaped cutters that pull on the fibers and then shear them. When using scissors to cut aramid fabric or prepreg, they must have a shearing edge on one blade and a serrated or grooved surface on the other. These serrations hold the material from slipping. Sharp blades should always be used as they minimize fiber damage. Always clean the scissor serrations immediately after use so the uncured resin does not ruin the scissors. Always use safety glasses and other protective equipment when using tools and equipment. Cutting equipment. The bandsaw is the equipment that is most often used in a repair shop for cutting composite materials. A toothless carbide or diamond-coated saw blade is recommended. A typical saw blade with teeth does not last long if carbon fiber or fiberglass is cut. Figure 788. Air-driven hand tools, such as routers, saber saws, die grinders, and cutoff wheels can be used to trim composite parts. Carbide or diamond-coated cutting tools produce a better finish and they last much longer. Specialized shops have ultrasonic, waterjet, and laser cutters. These types of equipment are numerical controlled (NC) and produce superior edge and hole quality. A water jet cutter cannot be used for honeycomb structure because it introduces water in the part. Do not cut anything else on equipment that is used for composites because other materials can contaminate the composite material. Prep-reg materials can be cut with a CNC Gerber table. The use of this equipment speeds up the cutting process and optimizes the use of the material. Design software is available that calculates how to cut plies for complex shapes. Figures 7, 89. Repair safety. Advanced composite materials including prep-reg, resin systems, cleaning solvents, and adhesives could be hazardous, and it is important that you use personal protection equipment. It is important to read and understand the safety data sheets, SDS, and handle all chemicals, resins, and fibers correctly. The SDS lists the hazardous chemicals in the material system, and it outlines the hazards. The material could be a respiratory irritant or carcinogenic, or another kind of dangerous substance. End of page 7 to 52. Eye protection. Always protect eyes from chemicals and flying objects. Wear safety glasses at all times and, when mixing or pouring acids, wear a face shield. Never wear corrective contact lenses in a shop, even with safety glasses. Some of the chemical solvents can melt the lenses and damage eyes. Dust can also get under the lenses, causing damage. Respiratory protection. Do not breathe carbon fiber dust and always ensure that there is a good flow of air where the work is performed. Always use equipment to assist in breathing when working in a confined space. Use a vacuum near the source of the dust to remove the dust from the air. When sanding or applying paint, you need a dust mask or a respirator. A properly fitted dust mask provides the protection needed. For application of paints, a sealed respirator with the correct filters or a fresh air supply respirator is required. Downdraft tables. A downdraft table is an efficient and economical device for protecting workers from harmful dust caused by sanding and grinding operations. The tables are also useful housekeeping tools because the majority of particulate material generated by machining operations is immediately collected for disposal. Downdraft tables should be sized and maintained to have an average face velocity between 100 and 150 cubic feet per minute. The downdraft table draws contaminants like dust and fibers away from the operator's material. Downdraft tables should be monitored and filters changed on a regular basis to provide maximum protection and particulate collection. Skin protection. During composite repair work, protect your skin from hazardous materials. Chemicals could remain on hands that burn sensitive skin. Always wear gloves and clothing that offer protection against toxic materials. Use only approved gloves that protect skin and do not contaminate the composite material. Always wash hands prior to using the toilet or eating. Damaged composite components should be handled with care. Single fibers can easily penetrate the skin, splinter off, and become lodged in the skin. Fire protection. Most solvents are flammable. Close all solvent containers and store in a fireproof cabinet when not in use. Make sure that solvents are kept away from areas where static electricity can occur. Static electricity can occur during sanding operations or when bagging material is unrolled. It is preferable to use air-driven tools. If electric tools are used, ensure that they are the enclosed type. Do not mix too much resin. The resin could overheat and start smoking caused by the exothermic process. Ensure that a fire extinguisher is always nearby. Transparent plastics. Plastics cover a broad field of organic synthetic resin and may be divided into two main classifications: thermoplastics and thermosetting plastics. Thermoplastics may be softened by heat and can be dissolved in various organic solvents. Acrylic plastic is commonly used as a transparent thermoplastic material for windows, canopies, etc. Acrylic plastics are known by the trade names of lucite or plexiglass and by the British as perspex, and meet the military specifications of MALP 5425 for regular acrylic and MALP 8184 for craze-resistant acrylic. B. Thermosetting plastics do not soften appreciably under heat but may char and blister at temperatures of 240 to 260 degrees Celsius, 400 to 500 degrees Fahrenheit. Most of the molded products of synthetic resin composition, such as phenolic, urea formaldehyde, and melamine formaldehyde resins, belong to the thermosetting group. Once the plastic becomes hard, additional heat does not change it back into a liquid as it would with a thermoplastic. Optical considerations. Scratches and other types of damage that obstruct the vision of the pilots are not acceptable. Some types of damage might be acceptable at the edges of the windshield. Identification. Storage and handling. Because transparent thermoplastic sheets soften and deform when they are heated, they must be stored where the temperature never becomes excessive. Store them in a cool, dry location away from heating coils, radiators, or steam pipes, and away from such fumes as are found in paint spray booths or paint storage areas. Keep paper masked transparent sheets out of the direct rays of the sun, because sunlight accelerates deterioration of the adhesive, causing it to bond to the plastic and making it difficult to remove. Store plastic sheets with the masking paper in place, in bins that are tilted at a 10 degrees angle from the vertical to prevent buckling. If the sheets are stored horizontally, take care to avoid getting dirt and chips between them. Stacks of sheets must never be over 18 inches high, with the smallest sheets stacked on top of the larger ones so there is no unsupported overhang. Leave the masking paper on the sheets as long as possible, and take care not to scratch or gouge the sheets by sliding them against each other or across rough or dirty tables. End of page 7 to 53. Store formed sections with ample support so they do not lose their shape. Vertical nesting should be avoided. Protect formed parts from temperatures higher than 120 degrees Fahrenheit 49 degrees Celsius, and leave their protective coating in place until they are installed on the aircraft. Forming procedures and techniques. Transparent acrylic plastics get soft and pliable when they are heated to their forming temperatures and can be formed to almost any shape. When they cool, they retain the shape to which they were formed. Acrylic plastic may be cold bent into a single curvature if the material is thin and the bending radius is at least 180 times the thickness of the sheet. Cold bending beyond these limits impose so much stress on the surface of the plastic that tiny fissures or cracks, called crazing, form. Heating. Wear cotton gloves when handling the plastic to eliminate finger marks on the soft surface. Before heating any transparent plastic material, remove all of the masking paper and adhesive from the sheet. If the sheet is dusty or dirty, wash it with clean water and rinse it well. Dry the sheet thoroughly by blotting it with soft absorbent paper towels. For the best results when hot forming acrylics, adhere to the temperatures recommended by the manufacturer. Use a forced air oven that can operate over a temperature range of 120 to 374 degrees Fahrenheit, 49 to 190 degrees Celsius. If the part gets too hot during the forming process, bubbles may form on the surface and impair the optical qualities of the sheet. For uniform heating, it is best to hang the sheets vertically by grasping them by their edges with spring clips and suspending the clips in a rack. Figure 7:90. If the piece is too small to hold with clips, or if there is not enough trim area, lay the sheets on shelves or racks covered with soft felt or flannel. Be sure there is enough open space to allow the air to circulate around the sheet and heat it evenly. Small forming jobs, such as landing light covers, may be heated in a kitchen baking oven. Infrared heat lamps may be used if they are arranged on 7 to 8 inch centers and enough of them are used in a bank to heat the sheet evenly. Place the lamps about 18 inches from the material. Never use hot water or steam directly on the plastic to heat it because this likely causes the acrylic to become milky or cloudy. Forms. Heated acrylic plastic molds with almost no pressure, so the forms used can be of very simple construction. Forms made of pressed wood, plywood, or plaster are adequate to form simple curves, but reinforced plastic or plaster may be needed to shape complex or compound curves. Since hot plastic conforms to any waviness or unevenness, the form used must be completely smooth. To ensure this, sand the form and cover it with soft cloth, such as outing flannel or billiard felt. The mold should be large enough to extend beyond the trim line of the part, and provision should be made for holding the hot plastic snug against the mold as it cools. A mold can be made for a complex part by using the damaged part itself. If the part is broken, tape the pieces together, wax or grease the inside so the plaster does not stick to it, and support the entire part in sand. Fill the part with plaster and allow it to harden, and then remove it from the mold. Smooth out any roughness and cover it with soft cloth. It is now ready to use to form the new part. Forming methods. Simple curve forming. Heat the plastic material to the recommended temperature, remove it from the heat source, and carefully drape it over the prepared form. Carefully press the hot plastic to the form and either hold or clamp the sheet in place until it cools. This process may take from 10 to 30 minutes. Do not force cool it. Compound curve forming. Compound curve forming is normally used for canopies or complex wingtip light covers, and it requires a great deal of specialized equipment. There are 4 commonly used methods, each having its advantages and disadvantages. Stretch forming. Preheated acrylic sheets are stretched mechanically over the form in much the same way as is done with the simple curved piece. Take special care to preserve uniform thickness of the material, since some parts must stretch more than others. End of page 7 to 54. Male and female die forming. Male and female die forming requires expensive matching male and female dies. The heated plastic sheet is placed between the dies that are then mated. When the plastic cools, the dies are opened. Vacuum forming without forms. Many aircraft canopies are formed by this method. In this process, a panel, which has cut into it the outline of the desired shape, is attached to the top of a vacuum box. The heated and softened sheet of plastic is then clamped on top of the panel. When the air in the box is evacuated, the outside air pressure forces the hot plastic through the opening and forms the concave canopy. It is the surface tension of the plastic that shapes the canopy. Vacuum forming with a female form. If the shape needed is other than that which would be formed by surface tension, a female mold or form must be used. It is placed below the plastic sheet and the vacuum pump is connected. When air from the form is evacuated, the outside air pressure forces the hot plastic sheet into the mold and fills it. Sawing and drilling. Sawing. Several types of saws can be used with transparent plastics, however, circular saws are the best for straight cuts. The blades should be hollow ground or have some set to prevent binding. After the teeth are set, they should be side dressed to produce a smooth edge on the cut. Bandsaws are recommended for cutting flat acrylic sheets when the cuts must be curved or where the sheet is cut to a rough dimension to be trimmed later. Close control of size and shape may be obtained by bandsawing a piece to within 1/16 inch of the desired size, as marked by a scribed line on the plastic, and then sanding it to the correct size with a drum or belt sander. Drilling. Unlike soft metal, acrylic plastic is a very poor conductor of heat. Make provisions for removing the heat when drilling. Deep holes need cooling, and water-soluble cutting oil is a satisfactory coolant since it has no tendency to attack the plastic. The drill used on acrylics must be carefully ground and free from nicks and burrs that would affect the surface finish. Grind the drill with a greater included angle than would be used for soft metal. The rake angle should be 0 in order to scrape, and not cut. The length of the cutting edge, and hence the width of the lip, can be reduced by increasing the included angle of the drill. Figure 7.91. Whenever holes are drilled completely through acrylic, the standard twist drill should be modified to a 60 degrees tip angle, the cutting edge to a 0 rake angle, and the back lip clearance angle increased to 12 to 15 degrees. Drills specially modified for drilling acrylic are available from authorized distributors and dealers. The patented Unibit is good for drilling small holes in aircraft windshields and windows. Figure 7.92. It can cut holes from 1/8 to half an inch in 1/32 inch increments and produces good smooth holes with no stress cracks around their edges. Cementing. Polymerizable cements are those in which a catalyst is added to an already thick monomer polymer syrup to promote rapid hardening. cement PS30 and Weldon 40 are polymerizable cements of this type. They are suitable for cementing all types of plexiglass acrylic cast sheet and parts molded from plexiglass molding pellets. At room temperature, the cements harden, polymerize, in the container in about 45 minutes after mixing the components. They harden more rapidly at higher temperatures. The cement joints are usually hard enough for handling within 4 hours after assembly. The joints may be machined within 4 hours after assembly, but it is better to wait 24 hours. End of page 7 to 55. Application of cement. PS30 and Weldon 40 joints retain excellent appearance and color stability after outdoor exposure. These cements produce clear, transparent joints and should be used when the color and appearance of the joints are important. PS30 and Weldon 40 should be used at temperatures no lower than 65 degrees Fahrenheit. If cementing is done in a room cooler than 65 degrees Fahrenheit, it requires a longer time to harden and the joint strength is reduced. The cement should be prepared with the correct proportions of components as given in the manufacturer's instructions and thoroughly mixed, making sure neither the mixing container nor mixing paddle adds color or affects the hardening of the cement. Clean glass or polyethylene mixing containers are preferred. Because of their short pot life, approximately 45 minutes, cement PS30 and Weldon 40 must be used quickly once the components are mixed. Time consumed in preparation shortens the effective working time, making it necessary to have everything ready to be cemented before the cements are mixed. For better handling, pour cement within 20 minutes of mixing. For maximum joint strength, the final cement joint should be free of bubbles. It is usually sufficient to allow the mixed cement to stand for 10 minutes before cementing to allow bubbles to rise to the surface. The gap joint technique can only be used with colorless plexiglass acrylic or in cases where joints are hidden. If inconspicuous joints in colored plexiglass acrylic are needed, the parts must be fitted closely, using closed V-groove, butt, or arc joints. Cement forms, or dams, may be made with masking tape as long as the adhesive surface does not contact the cement. This is easily done with a strip of cellophane tape placed over the masking tape adhesive. The tape must be chosen carefully. The adhesive on ordinary cellophane tape prevents the cure of PS30 and Weldon 40. Before actual fabrication of parts, sample joints should be tried to ensure that the tape system used does not harm the cement. Since it is important for all of the cement to remain in the gap, only contact pressure should be used. Bubbles tend to float to the top of the cement bead in a gap joint after the cement is poured. These cause no problem if the bead is machined off. A small wire, not copper, or similar object may be used to lift some bubbles out of the joint. However, the cement joint should be disturbed as little as possible. Polymerizable cements shrink as the cement hardens. Therefore, the freshly poured cement bead should be left above the surfaces being cemented to compensate for the shrinkage. If it is necessary for appearances, the bead may be machined off after the cement has set. Repairs. Whenever possible, replace, rather than repair, extensively damaged transparent plastic. A carefully patched part is not the equal of a new section, either optically or structurally. At the first sign of crack development, drill a small hole with a number 30 or a 1/8 inch drill at the extreme ends of the cracks. Figure 793. This serves to localize the cracks and to prevent further splitting by distributing the strain over a large area. If the cracks are small, stopping them with drilled holes usually suffices until replacement or more permanent repairs can be made. Cleaning. Plastics have many advantages over glass for aircraft use, but they lack the surface hardness of glass, and care must be exercised while servicing the aircraft to avoid scratching or otherwise damaging the surface. Clean the plastic by washing it with plenty of water and mild soap, using a clean, soft, grit-free cloth, sponge, or bare hands. Do not use gasoline, alcohol, benzene, acetone, carbon tetrachloride, fire extinguisher or de-icing fluids, lacquer thinners, or window cleaning sprays. These soften the plastic and cause crazing. End of page 7 to 56. Plastic should not be rubbed with a dry cloth since it is likely to cause scratches and to build up an electrostatic charge that attracts dust particles to the surface. If, after removing dirt and grease, no great amount of scratching is visible, finish the plastic with a good grade of commercial wax. Apply the wax in a thin, even coat and bring to a high polish by rubbing lightly with a soft cloth. Polishing. Do not attempt hand polishing or buffing until the surface is clean. A soft, open-type cotton or flannel buffing wheel is suggested. Minor scratches may be removed by vigorously rubbing the affected area by hand, using a soft clean cloth dampened with a mixture of turpentine and chalk, or by applying automobile cleanser with a damp cloth. Remove the cleaner and polish with a soft, dry cloth. Acrylic and cellulose acetate plastics are thermoplastic. Friction created by buffing or polishing too long in one spot can generate sufficient heat to soften the surface. This condition produces visual distortion and should be avoided. Windshield installation. Use material equivalent to that originally used by the manufacturer of the aircraft for replacement panels. There are many types of transparent plastics on the market. Their properties vary greatly, particularly expansion characteristics, brittleness under low temperatures, resistance to discoloration when exposed to sunlight, surface checking, etc. Information on these properties is in MIL HDBK 17, Plastics for Flight Vehicles, Part 2 Transparent Glazing Materials. These properties are considered by aircraft manufacturers in selecting materials to be used in their designs, and the use of substitutes having different characteristics may result in subsequent difficulties. Installation procedures. When installing a replacement panel, use the same mounting method employed by the manufacturer of the aircraft. While the actual installation varies from one type of aircraft to another, consider the following major principles when installing any replacement panel. 1. Never force a plastic panel out of shape to make it fit a frame. If a replacement panel does not fit easily into the mounting, obtain a new replacement or heat the whole panel and reform. When possible, cut and fit a new panel at ordinary room temperature. 2. In clamping or bolting plastic panels into their mountings, do not place the plastic under excessive compressive stress. It is easy to develop more than 1000 psi on the plastic by over-torquing a nut and bolt. Tighten each nut to a firm fit, and then back the nut off one full turn until they are snug and can still be rotated with the fingers. 3. In bolted installations, use spacers, collars, shoulders, or stop nuts to prevent tightening the bolt excessively. Whenever such devices are used by the aircraft manufacturer, retain them in the replacement installation. It is important that the original number of bolts, complete with washers, spacers, etc., be used. When rivets are used, provide adequate spacers or other satisfactory means to prevent excessive tightening of the frame to the plastic. 4. Mount plastic panels between rubber, cork, or other gasket material to make the installation waterproof, to reduce vibration, and to help to distribute compressive stresses on the plastic. 5. E-plastics expand and contract considerably more than the metal channels in which they are mounted. Mount windshield panels to a sufficient depth in the channel to prevent it from falling out when the panel contracts at low temperatures or deforms under load. When the manufacturer's original design permits, mount panels to a minimum depth of 11/8 inches, and with a clearance of 1/8 inch between the plastic and bottom of the channel. 6. In installations involving bolts or rivets, make the holes through the plastic oversize by 1/8 inch in center so that the plastic does not bind or crack at the edge of the holes. The use of slotted holes is also recommended. End of page 7 to 57. End of chapter 7. Chapter 8 is coming soon.